Hi, Mr. Richards here. Today's lesson is on polygons, and our objectives are to classify polygons, determine the sum of the measures of the interior angles of a polygon. Our first step is to define what a polygon is, and it is a simple, closed figure formed by three or more line segments called sides. And sometimes the best way of figuring out what a polygon is to describe what a polygon is not. So these are examples of things that are not polygons. I mean, if I have a shape, I can have a shape that's made up of 3 line segments or even 4, but it's not closed. So it is not a polygon. Or I could have something that looks a bit like this that is closed, but we have overlapping sides. So it's not a polygon because the sides overlap. And lastly, I could have a closed figure made up of line segments here, but if there's a curve involved, it's not a polygon. So a simple closed figure formed by 3 or more line segments called sides is a polygon. If it's not closed, has overlapping sides, or has a curve with it, since a curve is not a line segment, these are non-polygons. Now, polygons can be classified by the number of sides they have. For example, if you have 3 sides, this is a triangle. 4 sides, quadrilateral. 5 sides is a pentagon. 6, hexagon. 7, heptagon. 8, octagon. 9, nonagon. And 10, decagon. Now, in our first example, determine whether the figure is a polygon. If it is, classify the polygon. If it is not a polygon, explain why. Well, let's go back to our definition. A simple closed figure formed by 3 or more line segments. Well, I have 1, 2, 3, 4, 5. It is closed. And so let's go through our non-polygons. Well, not closed, that doesn't fit. Overlapping sides, I don't have any overlapping sides. And there's no curve involved, so it fits the definition of a polygon and doesn't hit any of our non-polygon things, so it is a polygon. So the figure is closed and has 5 sides that only intersect at their endpoints. Now, how many sides were there? Well, we said 5. And to classify this, it is a pentagon. One of our key concepts today involves the interior angles of a polygon. And what we can say in words is that the sum of the degree measures of the interior angles of a polygon with n sides is, parentheses, n minus 2 multiplied by 180. Now, a diagonal is a line segment that joins two non-consecutive vertices in a polygon. Now, if we take something like a quadrilateral, a four-sided object, if we start at this vertice, non-consecutive vertices means I'm not going to go out to that and I'm not going to go out to that vertice. The only non-consecutive vertice is coming out here to right there. If I take something a little fancier like a pentagon, and if I were to start here, my consecutive vertices would be here and there, so it's not going to connect there, but it's going to come down here like so. Now, if we examine this, we learned in our last lesson that the number of degrees in a triangle is 180 degrees. So what is formed when we draw these diagonals? Well, in our quadrilateral, we have two triangles. We have four sides and two triangles. What do we have with our pentagon? We have five sides and three triangles. Well, if we hop back up to that formula, n minus 2 times 180, remember, the sum of the angles in a triangle add up to 180 degrees. And notice, we have four sides in our quadrilateral, but two triangles. Well, if we put that into the formula, 4 minus 2 is the two triangles times 180. For the pentagon, 5 sides minus 2 are the three triangles times 180. So basically what our formula is telling us is that the number of sides minus 2 indicates the number of triangles formed going from one vertice. Now, find the sum of the measure of the interior angles of a heptagon. Well, if we kind of go the old-fashioned drawing diagonals method, if we just pick a vertice there and draw as many diagonals as we can, and go to here, and here, and here, and lastly, over here. And so we have a total of 1, 2, 3, 4, 5 triangles that are formed. And so one way of solving this without the formula is just to say I have 5 triangles. So I could take 180 and multiply it by 5 to get 900 degrees. Now say you didn't have the shape here. What you could use is our n minus 2 times 180. And this is what I'm going to encourage you to use with this lesson. The number of sides in a heptagon are 7. And so we'll substitute that 7 in for n, 7 minus 2 times 180. And notice, that just gets us the 5 times 180 again, which is 900 degrees. And so the way you'll be solving these problems today involves the n minus 2 times 180, but this over here is proof on why that works. The definition of a regular polygon is a polygon that has all sides and all angles congruent, meaning they're all equal to each other. All the side lengths and all the angles are equal to each other. And so what we can do, we can look at a regular octagon like a stop sign. What is the measure of one interior angle in a stop sign? Well, we can use our little formula here, n minus 2 times 180. Now, our octagon has 8 sides, and so we'll substitute in that 8 for n, and result in 6 times 180. And 6 times 180 is 1,080. Now that is the total sum of the measures of the interior angles. What I'm going to do with this now, since all the angle measures inside a regular polygon are equal, I'm going to divide this by my number of sides then, and angles then, 8. My result is 135 degrees. And in our last example today, we have tessellations. Now, a tessellation is a repetitive pattern of polygons that fit together with no overlaps or holes. The sum of the measures of the angles where the vertices meet in a tessellation is 360 degrees. And I can look at a quick example here of a tessellation. If I have a set of quadrilaterals, these do meet in the middle, and each one of these little angles is 90 degrees. And so the 90 plus 90 plus 90 plus 90 is 360 degrees. Another way of looking at this is saying, all right, one of the interior angles of a quadrilateral is 90 degrees. Can I take 360, divide it by that 90 degrees, and get an even number? Well, yes, I get 4. So if you can take the interior angle of a regular polygon, and if that is divisible by 360 degrees, then you can form a tessellation with that shape. And so we have 2 examples here. Determine whether or not a tessellation can be created using only regular decagons. If not, explain why. Our first step is to find the measure of one interior angle of a decagon. And so we can use our formula, n minus 2 times 180. Our decagon has 10 sides, so 10 minus 2 times 180. 8 times 180 is 1,440. Now when I divide that by 10, I get 144 degrees for each interior angle. So basically then, 144 times n needs to equal 360 degrees. And when I divide by the 144 on both sides, my result is 2 5/10. So this indicates that it is not divisible. So for our answer, what we can write is no. Each interior angle of a regular decagon measures 144 degrees and 360 degrees is not evenly divisible by 144 degrees. And so let's try that one more time. Determine whether or not a tessellation can be created using only regular triangles. If not, explain. We need to once again find the interior angles of one triangle. And so by using our formula, it should not be a surprise that a triangle's angles measure up to 180 degrees. And so if I take that 180 and divide by the 3 angles, I get 60 degrees. So each angle is 60 degrees. If I set 60n equal to 360, I can then divide by 60 on both sides, and I get n equals 6. Now since it divides evenly, I can say, well, yes, a regular triangle can be used to make a tessellation. And in fact, it would take 6 regular triangles to make a tessellation. And that is it for this lesson on polygons. Good luck.